Hello, this is the direct drive pedal team for ME 157. My name is Christian.
I'm Yvonne.
I'm Eddie.
And I'm Milani.
And I'm going to hand it off to Yvonne to introduce our project.
In our presentation today, we will be covering the background and purpose of our project. We will be going through our QFD and design specifications, kinematics and simulation, and finally our stress and cost analysis. Currently, there are 4 bass drum pedal designs on the market: chain drive, double chain drive, belt strap drive, and direct drive. Direct drive pedals are typically more expensive and are more durable, reliable, and high performing. These 3 pedals pictured here represent the average going cost for a direct drum pedal. The Tama Thindsing pedal in the middle being the cheapest at around $350, and the DWMDD being the most expensive at around $500. In this project, we set out to design a bass drum pedal that can deliver the exceptional feel and performance of a high-end pedal while at an affordable price to ensure accessibility to musicians at any level of expertise. Among the 3 basic types of pedals, chain, belt, and direct, we determined that the market is lacking an affordable direct pedal drive, as they are shown to deliver unparalleled performance but at a high cost. With custom-created parts that are inspired by pedals currently on the market, we incorporated key design elements and focused on streamlining the design to deliver in performance as well as affordability. Milani will now take over and talk about the QFD.
In order to design with our customer in mind, we performed a QFD, and this is the house of quality that we came up with in order to go over each customer requirement and therefore the correlating design requirement. This is overall the larger house of quality, but we will break it into different parts in order to go over the important aspects of each part. So to start off, our target consumer is the musician that will be playing the drum pedal. As you can see from the customer requirements, there are 4 major customer requirements that are the most important. The first one being the price, the affordability, which is what Yvonne talked about being the driver for this project in order to reduce the overall cost. The second is durability. We need a drum pedal that is going to be durable while the drummer is playing and not break on them in the middle of their show. The third and fourth are stability and latency. After we decided what customer requirements were the most important and also what should still be taken into account, we correlated these to the functional requirements. So as you can see at the top of the house of quality, there are different functional requirements that we decided the drum pedal would need to have. And then depending on the symbol that is placed next to these, we correlated them to the customer requirements. So for example, for stability, it is heavily correlated to the force required to depress the pedals to the bass drum head, which means that this will be the functional requirement, one of the functional requirements for the stability. We also then compared all of these functional requirements and customer requirements to the drum pedals that are on the market, and we're able to compare our product to the other ones on the market. Finally, we were able to decide which of these functional requirements were going to have the most weight for our design. And so as you can see, the footboard length and width are very important. This is because the smaller the drum pedal is, the less cost it will take to manufacture and the less cost of material there will be. Same thing with the material density. It is highly weighted, and that's also due to manufacturing costs. After going through the QFD and the house of quality, we came up with these design specifications that our drum pedal would need to have. The most important ones are the dimensions for the drum pedal. They need to fit within the maximum height, width, and length that is listed. The maximum weight is also very important. It can't be more than 6.5 pounds. And the most important is at the bottom, the total cost of the pedal, which should be around $150 to $199, which is significantly less than the competition. Now I will be passing it on to Christian to talk about the design.
By using the design specs as a guide, we began sketching out our pedal. Here are some of the sketches that we made early on in the design process. Once we had a good idea of how we wanted our pedal to look like, we began to consider the kinematics for our project. We started this by analyzing each component through reverse engineering. Then we found the average force of the input by weighing the pedal while it was in use and referencing the average kick force of a person. And throughout the 3D modeling process, we frequently tested the pedal in SolidWorks to ensure that the pedal geometry and sizing was functioning as intended. As mentioned before, we drew a lot of inspiration from other pedals, and one can observe this by looking at the details of each component. The direct drive linkages were heavily inspired by the configuration on the Pearl Eliminator, as we deemed it the most elegant and simple design currently on the market. The footboard from the is derived from the DW900 pedal, as the whole pattern provides the perfect amount of grip and friction and would be easily machined, thus keeping costs low. Lastly, the rest of the components, namely the spring assembly, hoop clamp, and the pillars, were pulled from the Tama Iron Cobra pedal, as they have some of the most robust designs. Here's a simulation that we performed in SolidWorks, and it's oscillating from the starting and the end position. Next, I'm going to hand it off to Eddie to talk about some stress analysis.
With some difficulty using FEA, we decided to perform stress analysis on the most critical components. We started with stress analysis on the foot pedal since it receives direct contact with the user's foot. From research, a driver on average applies 70 pounds of force on the gas pedal. We went with a little bit more lenient 50 pounds or 500 newtons, which is still comfortably over our design spec. In selecting heat-treated machine 6061 aluminum, we found the factor of safety to be 3.49. This was a comfortable number, and using aluminum proved to be a good choice for preventing the part from failing while being lightweight, as the footboard is quite big in terms of volume. The flange that supports the spring anchor is also a 6061 aluminum and was subjected to constant bending since the spring is constantly providing the tension. We calculated that it would have a 3.86 factor of safety and will not fail under normal usage. The beater rod was also subjected to constant bending when striking the surface of the drum, and for something quite small in diameter, we went with a surgical grade 316L steel, which worked out to have a 22.75 factor of safety. We also used this same steel for the shaft, and because there were many different size diameters, we decided to perform stress analysis on 4 sections to accommodate for the stress concentrations. And we may have ran into some hiccups during the calculations, because although none of the sections would fail, they all achieved very high factors of safety, with the lowest one being 250.36. And finally, we determined that the 4 small single-row deep groove 8mm bore bearings in the pillars that would support the shaft would be critical components. And to give benefit of the doubt, we researched that the world record for the most beats in a minute was a little over 1400. And using that and the arc that the beater travels from initial to final position, we calculated that the bearings would be performing at 117 revolutions per minute. And we determined that the bearings would last around 36 mega hours, which would be a lifetime, even when used very harshly.
The fundamental purpose of our project was to create an affordable direct drive pedal that could compete against a high-end model. After thorough researching, it was decided that McMaster-Carr was the best place to purchase relatively low-cost quality materials, most of which was 6061 alloy aluminum that would then be machined to spec. It is important to note that the price for each material or component required for the drum pedal would be more cost-effective if ordered in bulk. Manufacturing was assumed to be done at SJSU's machining facilities, running the cost of manufacturing down to zero. Were this drum pedal mass-produced, it would have been beneficial to use mass production processes such as injection molding, casting, automated milling, and lathing. The overall total cost for manufacturing our drum pedal came out to approximately $220. Our aim was to drastically bring down the cost of quality drum pedals from approximately $500, and in this we were successful. that was our presentation. Thank you.